So we're going to do a fairly common physics problem that is useful in terms of seeing how both friction and circular motion work, but then also how we use force diagrams. This gets a little complicated as we go, but it's mostly just complicated in the algebra piece. So we're going to start with the situation of a car on an angle. This is going sort of into the page, going around, say, a curved track. So this is a banked angle, and we're going to use the data from the Daytona 500 track where this bank is 31 degrees and the radius of the curve is 305 meters. And so what we're going to do is first look at sort of what the ideal speed is where we don't need any friction to go ahead and go around this curve at this banked angle. And so what we've got is we've got weight that's down, right? mg that's down. We have normal that's in this direction. Again, I don't know if this is to scale yet. We'll fix it. This is force normal. And if we don't need friction to make this happen, these are the forces that we have. But notice we're going around a circle and we're going to be pointed towards the center of the circle. So at least in this diagram, this is an acceleration towards the center this way on sort of a coordinate system that's centered here. And so what that tells me for my coordinate system is that I don't want a tilted angle. I'm going to make it orange. Actually, because my acceleration is towards the center this way, it's not down the track, then I'm going to set this up as my x and my y axis. And so we're going to just have these forces and see what happens. And so if this is my angle theta here, then we can make the argument, in fact, that this right here is theta, because if theta is flat or 0, then the normal force lines back up like that. And if we tilt it all the way up at 90 degrees, then the force normal would be sort of pointing along the x-axis, but at that point we would have a different situation. You could still have something going around a straight banked path. It's just a different situation. So this is our setup like this. And if you're not sure about this, you can of course go through and say this is the angle, say alpha, and then you can recognize, okay, then the angle between this point and this point is theta, which makes this angle alpha, which makes that one theta again. So you can do it that way as well. Okay, I want to get rid of some of these because this is going to get to be a messy force diagram just from where we are. Okay, so what that tells us is that if we break our force into components here, this y component, the normal y, is going to be, it's adjacent to this angle theta, and this is force normal x, that this force normal y, F normal y, is F normal then times cosine of theta, and F normal x, and these kind of weird axes, is F normal sine theta. So I've broken it into components according to this coordinate system. And what I can see right away is that my x component of this normal force is what's going to provide my acceleration. So if I do F equals ma into components, so I have the x component, and I have adding up all the forces equals mass times the acceleration in the x direction. That's going to tell me this is force normal x, which is force normal sine of theta, just coming from here, is equal to max. And in the y direction, I have force normal y is up minus mg is down, and I don't have any acceleration in that direction. And so that tells me that I can substitute in, let's see, for the green is going to be that right there. And so I'm going to say force normal cosine theta minus mg is equal to 0, or force normal cosine theta is equal to mg, force normal is equal to mg divided by cosine of theta. I've just done this algebra to kind of get at what my normal force is. I can then plug this in right over here, and I can find mg sine of theta over cosine theta, substituting things in, is equal to ax. And notice the m's cancel, which is convenient. And we just have that our ax is g sine theta over cosine theta, or our a is equal to v squared over r. And the question was, although I didn't write it down, so maybe it wasn't clear, what is the speed at which we're going to go around this track where we don't need friction? So we're really looking for our v squared term here. So if we plug this in to right here, we can stop at any point and put our numbers in, but this is fine. G, this is tangent of theta, is equal to v squared over r, or v is equal to square root of g times r times tangent of theta, which only works for this situation. I mean, every equation we get really is situation dependent, so I want you to keep that in mind. So if I plug this in for a theta of 31 degrees and a radius of 305 meters, I get a speed of right at, I calculate 42 meters per second, which is not too far off from about 100 miles an hour. Okay, so this, if we're going exactly at 42 meters per second, there's no friction needed to provide that acceleration to the center, which is different than like when we're going around a flat circle. We must have that static friction pointing towards the center. So you can already see how a banked situation allows you to not need some friction. But on the Daytona Speedway, cars, I think, go faster than this 42 meters per second. So I want to pick a value that's bigger than that and see what happens, see what we need in terms of friction. So this was sort of part one. Part one was speed without friction. Now we're going to have the same type of diagram for part two. So I'm going to repeat this. Again, I have this angle, have the car. Oops. And here's theta. And what we're going to do is we're going to increase our acceleration. So part two, our v around the track goes up, and so our acceleration goes up. And so this acceleration now is bigger towards the center. So I need a force that's bigger towards the center than I already have. And so I already had the normal force, which was some amount towards the center. And so now I need some frictional force to help me out. Okay, so the way I'm going to look at this is I'm going to set up, friction is of course along the surface, so I need to say my frictional force, my static friction, again, this is across the tire, so it is static as long as we're not sliding up or down the track, but we're just going along the track in a straight direction at the same height, basically, around the track. You don't want to slide and skid, obviously, at speeds higher than 100 miles an hour. So we've got friction going down that way to oppose the sliding up the track, and we still have our normal force like this, and our acceleration is still towards the center here. So that's our acceleration. So we still want our axis to point like this. Okay, and our weight is still down like this. This is our mg. So I'm going to redraw this axis because it's kind of hard to see with the car there. But there's my mg. My normal force is off like this. That's force normal. It's unknown. It's just adjusting, right? But this, just from what we did before, that is our angle theta, the angle of the track. And notice if this is our angle theta right here, blow this up just a little bit. And this is sort of parallel to it. Then by parallel angles, this is also going to be theta. So we can draw, which makes sense because then that makes this, if this is theta, then that makes sense because this makes that 90 degrees. So all of this geometry works out. So this is static friction, this is the normal force, and this is mg. So my question for this is we've increased the speed, and what we want to know is what is the smallest coefficient of friction that will allow this to happen, that we can make it around the curve without sliding up or down. So what is our mu sub s, where we have f of s is equal to mu s times force normal. That's our maximum value for this friction, so that we make it around the curve. In other words, so that this force diagram works, that we're still looking at static friction and everything like that works out. So let's pick a number. I'm going to pick a number in this problem. Make it around the curve, let's say at, what did I use? 70 meters per second, which is about 157, 160 miles per hour. Okay? All right, so that's what we're going to find out to see if this is anything like a reasonable number. So again, I'm going to do my x and y components, but here I've got lots of trig that's going on, right? So my normal force, I still have the same thing I had before. Force normal in the x is force normal sine theta. Force normal in the y is force normal cosine theta. And then for friction, I've got the same kind of thing going on. I've got force, static friction in the x direction is equal to force of friction. The x direction is the adjacent, right? So that is cosine of theta. And force S in the y is Fs sine of theta. And so we've got all of our components. So I'm going to do adding up the sum of the forces in the x direction, which will equal m times the acceleration in the x direction, and sum of the forces in the y direction, which is going to be 0, because this is our y and this is our x, and that was the whole point of picking this coordinate system, because we already know this acceleration. So if we set this up, we have now, just looking at our force diagram, force normal in the y, which is force normal cosine theta. The y component of friction is down, so it's minus Fs sine of theta minus mg is equal to 0. And over here in the x direction, I have force normal sine of theta plus force of friction cosine of theta. Both of those are pointing in the same direction as my acceleration. So it looks like that. Now this is kind of messy because I'm going to substitute in F sub s is equal to mu times n, because what we really wanted was our mu sub s. Right, so I'm going to put that in here and then in here. And I still have a number of unknowns. I mean, I know theta, but I don't know this and I don't know mass. So I've got to do a little bit of algebra with this. So I'm going to put this in, and I've got force normal sine theta plus mu force normal cosine theta is equal to ma. And similarly over here, force normal cosine theta minus mu force normal sine theta minus mg equals 0. And I'm going to have to do the rest of this in the very next video.